Okay, so I see everything now myself. Okay, I want to give you a short introduction to particle accelerators with a special emphasis on hadron colliders, since I know that you are all members of the STAR and ALICE collaborations, starting mostly, I believe, research careers. And I would like to, I think it's impossible to give you a complete survey of the vast field of particle accelerators, physics and technology, but I will give you what I hope will be a few keys to understanding the kinds of discussions that you will hear, and how these colliders, RIC and the LHC, work and provide beams to the experiments. So accelerator physics and the technology is a field that has made spectacular progress for just about a century now. The growth in energy of our machines has been far faster than the growth in size or cost, although both have been substantial. It's often been said that this progress has reached its limits. People were saying that when I started my career in the subject in the early 1980s. So I don't know, it may be true, but I think we should be optimistic and hope that people will continue to be ingenious and find new ways of getting to ever higher energies and performances. So although the timescales for these frontier energy projects are certainly becoming longer, we look forward to one or other of these future colliders, the ILC, the FCC, electron-positron, the Chinese machines, similar Chinese machines, the FCC Hadron Collider, perhaps a muon collider, perhaps one day plasma accelerators. But going back to the present and the next few years, the next, say, 10, 15 years, we as nuclear physicists are lucky to be living in an exciting time with the LHC in the middle of its program and RIC still running, but due to be reborn fairly soon as the electron-ion collider. So in these lectures, I'll mainly use LHC examples because that's the machine I'm most familiar with myself. However, some of you will be working, I believe, at RIC on STAR. RIC is a collider. It's 3.8 kilometers in circumference. It relies on superconducting magnets with a maximum field of 3.5 Tesla. Protons in this machine can reach an energy of 255 GeV. Heavy nuclei like gold to energies of 100 GeV per nucleon. And the species include polarized protons and quite a number of nuclear beams up to uranium. There are experiments like STAR and Phoenix, which is being transformed into S-Phoenix. The LHC at CERN looks like this. It's, okay, I'm speaking to you from about here. The weather isn't so good as it looks in this picture today. It's hard to believe there are mountains out there. But this machine, as I'm sure you know, has a circumference of almost 27 kilometers. It's operated so far with a maximum dipole field of about 7.7 Tesla, but nominally can go to 8.3. Energies of protons 6.5 TeV and potentially up to 7, maybe even a little beyond ultimately. And for the lead beams, an energy per nucleon, which I prefer to write as with the factor A in the expression. So actually, formally, this is the total energy of the particle, which is 82 times the 6.5, about 500 TeV, of 2.56 TeV per nucleon. And the species collided so far include protons with protons, lead, proton lead, and xenon. And quite soon, we hope also to be colliding oxygen and proton oxygen. And the experiments, as you know, are ALICE and the others at the CMS, LHCb, all taking heavy ion collisions. There are also smaller experiments like LHCf and now Phaser and Totem and Modal. So accelerator physics, I'm assuming so far that you have not encountered this subject because It's not taught in many university degrees in physics. In a few places it is. I'm not sure what's the case in the universities in India. I would say that accelerator physics is in some sense a microcosm of the whole of physics. It's probably includes the most advanced applications of relativistic classical Hamiltonian dynamics of single particles. It's an application of flow-K theory in an especially elegant formalism, but includes nonlinear dynamics, questions of long-term stability, and this formalism is a fundamental tool for the design of particle accelerators. We often talk about the technologies of magnets, of RF accelerating cavities, but I think in the history and the history and the continuing success of circular machines and circular colliders owes a lot to the fundamental mathematics of dynamical systems, which doesn't have a cost or a construction development or anything like this, but it's been fundamental to our subject and the reason circular machines have an advantage over, for example, linear machines, in my opinion. Electromagnetism is obviously useful in many, many ways in the subject. As in the theory of the quark-gluon plasma, we also have to worry a great deal about the collective behavior of many charged particles. Intense beams interact electromagnetically with themselves. This is called direct space charge, and also through their surroundings by the fields they generate in them, the cavities, the vacuum chambers. And this is described with the concept of impedances and collective instabilities. I won't have time to talk about many of these things. The beams collide and interact with each other. There are electromagnetic forces between the beam, the so-called beam-beam effects. There are various subjects which can be considered statistical mechanics of beam distributions. A classical example is the Bjorken-Tingwa theory of intrabeam scattering, which is very important for our heavy ion beams. Not so much in hadron machines, but in electron machines, quantum physics determines the properties of a beam. There's lots of plasma physics in things like plasma wake field accelerators and analogies with the collective instabilities. Superconductivity, as of course for the magnets, the RF accelerating systems, and particularly for heavy ion beams, nuclear physics interferes quite directly in performance limits for our ultra relativistic heavy ion beams. I'll talk a little about that tomorrow. It's a big field. There are many types, many applications of accelerators. They are basically our main tool for accessing the subatomic world. We concentrate energy in tiny volumes, whether those are atomic volumes or nuclear volumes, as at the LHC and RIC, where the concentration of energy is quite phenomenal when you calculate it. There are many applications: elementary particle physics, of course, colliders and fixed target, nuclear physics, which increasingly uses exactly the same tools, synchrotron light sources. These are storage rings which have many applications in material science, medicine, archaeology, and so on. Neutron sources, medicine, you've all heard about cancer therapy, radioisotopes, food processing. And of course, there are many technological spin-offs. I won't discuss accelerator technology, there's simply not time. But I'll try to give you some keys to understanding the discussions related to the LHC collider. And I'll try to not be superficial, but go as quickly as possible to some non-trivial understanding of the concepts. In particular, in lecture 1, we're going to do a little bit of mathematics in the subject of transverse dynamics to understand the basics of the strong focusing principle, the ideas of beam optics and emittance, and I'll illustrate them with the LHC, particularly the Alice interaction region. I believe this contains some of the most important principles that you should understand. I don't want to prevent it superficially. I want to convey a little understanding, I hope. In lecture 2, will be more broad-ranging. I'll talk about nuclear beams, the ideas of luminosity, the energy of the collisions, the limits to performance in heavy ion collisions, the filling schemes and hadron colliders, the evolution of the program so far, and the outlook for the LHC. So You can learn more, of course, with in more time. I'd like to point out the Joint Universities Accelerator School, which occurs in Europe near to CERN. I was formerly the director of the school. They are at present taking applications for 2 5-week courses in accelerators, the science and the technology. At the beginning of next year, if you have a strong interest, you could register now for these online courses. For the moment, because of the pandemic, they are given entirely online. You don't need to travel to the Archon campus. So it's possibly an opportunity, although a bit of a disadvantage compared with the usual courses and where you travel there and visit labs and so on. There's also the CERN Accelerator School, which has many resources, and the US Particle Accelerator School. A few favorite textbooks. Edwards and Cyphers is a very nice, popular introduction. An advanced book on the level of Jackson's Classical Electrodynamics, which you probably know, is the book by S.Y. Lee, which I recommend highly. There's also a popular book by Helmut Wiedemann, which is bigger, very comprehensive. Neither of these books actually say too much about colliders, but they cover the basics very well. Another popular book is the Handbook of Accelerated Physics and Technology, which we all keep right on our desks for reference. It's a comprehensive vademecum, and there are many others, of course. So let's get started. I'll talk about the transverse dynamics of single particles in a machine. Well, it's all about focusing. And why do we need focusing? Here's an extremely naive piece of reasoning. We know that the momentum and the magnetic field and the bending radius of a particle are related by this simple formula, which can be written numerically like this and with the units. So for a change in momentum, if you have a small spread in momentum in the beam, you have a similar change in the bending radius. In a particle collider such as the LHC, the spread in momentum is 10 to the minus 4 to 10 to the minus 3, which would give you a spread in radius of about 3 meters, which if you look at the LHC beam pipe, which is about 47 millimeters wide, that's not going to fit. So you have to do something better. The beam pipe would actually have to be larger than the tunnel. So somewhere along the line, somebody had a better idea, which is the strong focusing principle, which I'll now try to explain. First, let's look at the coordinate system used in accelerator physics. It's a rather special one. We start with the idea of a reference particle which has a fixed momentum p0, which follows an ideal reference orbit O, which is a curve in space with locally a certain bending radius corresponding to that momentum p0 and the local magnetic field. This curve is parameterized with the coordinate s, which is arc length along that curve starting from 0 at some point, which happens to be the Atlas interaction point in the LHC. And this is called the reference orbit because a particle which had just this momentum would follow it if you started it with 0 deflection angle with respect to the orbit, so it was at a tangent. But then if it's not quite on the reference orbit, we describe its horizontal displacement with a coordinate x, its vertical displacement with a coordinate y. And there is the third coordinate, which I'm not going to really specify precisely, but it's actually the, well, in Cartesian coordinates, it's locally the value of s. So there's an orthonormal set of axes here. But this set of axes slides along the curve as the particle moves along, as the reference particle moves along S. And it may be that it falls a little bit behind another particle, a general particle might fall a little bit behind or get a little bit ahead of the reference particle. So the time t becomes the coordinate for the third degree of freedom. It's because different particles pass S at different times. And we usually use the time delay with respect to the reference particle as the third coordinate. Okay, So each of these coordinates, x, y, and usually it's ct to have the same dimensions, has a conjugate momentum variable. So these are measured in units of the nominal momentum, so they are dimensionless and approximately equal to the angles of the particle with respect to the reference trajectory. So, of course, this curve is not exactly a circle. You can start with a circular accelerator which is entirely full of bending magnets with the same magnetic field. You can cut it like this and insert a couple of straight sections here, or perhaps 3, 4, 5, 6, 7, or 8, as in the LHC, and join these pieces with straight sections. Moreover, O need not lie in the horizontal plane if the ring is not flat. If there are vertical bends somewhere, that's usually not the case, but it can be. So the insertions between the arcs allow us to insert other things between the magnets, for example, physics experiments, notably the biggest ones, the RF systems, the collimation, the beam dump. If you are used to the coordinate system in your experiment, like Alice, there is a coordinate system which usually has its origin at the interaction point. And at that point only, that particular value of S, it coincides with the detector system, although the orientation and the labels X, Y, and so on may be different. In fact, there are many other small straight sections in the arcs of the machine between the bending magnets, because we have to insert quadrupole focusing magnets or other types of magnets, beam instrumentation, vacuum pumps, and other devices. So you can't fill the ring with bending magnets, although you try to, because the more you fill it, the higher energy you can reach for a given size of tunnel. So let's take a look at the equations of motion. It's preferable to use a formal Hamiltonian dynamics approach, but I won't do that because I don't want to overload the presentation. So I'll use simple transformations of the Lorentz force equation for a particle moving in a magnetic field. Its position vector is given by R. We won't consider the longitudinal motion at the moment, just consider the transverse displacements. R is rho plus X, and these unit vectors for X and Y are, remember, moving along the trajectory and pointing in different directions as a function of S. So you can write the cross product out more explicitly like this. The energy, of course, is constant because we're only considering magnetic fields. And we can formally calculate the time derivatives of R in these coordinates. If we take the X component of the equation of motion, it looks like this, where P0 over E is which is equal to the nominal magnetic field on the reference curve. B0 times the local bending radius is called the magnetic rigidity. I think you can, I'm perhaps going a little fast, but I think you can follow all the steps yourself later. I'll put the slides on Indico. If we transform now to S as the independent variable. Sorry, was there a question?
Was the last scheduled date?
I'm sorry, is somebody?
Tulika, can you please mute your microphone? Yeah.
By the way, if there is a pressing question, it's okay to interrupt through the chairman, perhaps with the chat or some. So if one transforms to S as the independent variable, like this, the rate of change of time coordinate with respect to S can be written like this. It's related to the stretching of the orbit by deviations from the reference orbit, and of course to the velocity of the particle in the longitudinal direction. So if the particle deviates, it takes a little longer to cover a distance S along the reference curve. And one can compute the second derivatives of X and Y, and you end up with quite similar equations. In the horizontal plane, the local vertical field, which depends on S, but also X and Y in principle, because the field can vary around the orbit, the reference orbit, and this orbit lengthening factor. Okay, so I didn't formally indicate the dimensions, but you know the magnetic fields as a function of X, Y, and S through field maps or multiple expansions. So these equations are quite nonlinear in general. And there's, of course, a sign difference between X and Y related to Maxwell's equations. In general, this simple change of variables is a special procedure in Hamiltonian mechanics where you change the independent variable from time to this arc length S. You may recall problems in classical mechanics where you do this. Old style examples are related to beads sliding on wires and things like this, but it's actually a very important and useful procedure in accelerator physics. You can see more about the details in the textbooks. So the focusing fields, well, we know that from Maxwell that curl B is 0, so there are relations between the gradients of the fields. And one can expand them around the reference curve like this. If we assume that the simple case of a planar ring, the horizontal field on the reference orbit is 0. And the vertical field, which is the bending field in the horizontal plane, is not 0, it's the B0 I mentioned before, typically. You also have the gradient, the quadrupole field, of a normal quadrupole. These two gradients, the derivative of bx with respect to y and the derivative of by with respect to x, are equal. And then you can have what we call a skew quadrupole, which is a quadrupole rotated about the direction of motion. But I'll assume those are 0 because they actually introduce coupling terms between the x and y motion. Which is a complication. It's something one has to deal with in reality, but I won't include that in this uncoupled treatment for the moment. So then the equations of motion can be written like this. You can see that there is a term involving the bending radius in the horizontal plane, which is absent in the vertical. This is called the weak focusing term, and early accelerators only depended on this. In modern separated function, strong focusing machines, you have the quadrupole fields, which are related in X and Y. So a quadrupole which focuses in the horizontal, defocuses in the vertical. Both of these equations are of the form X double prime, where primes denote derivatives with respect to S now, plus some gradient function K of S, which you can see here. Times X is equal to 0. K has the property that it's periodic in the circumference of the reference orbit. So this is a special equation. It's more complicated than a simple harmonic oscillator because of the dependence of the force constant on S. One way we typically solve it is through matrix solutions, which is, of course, the linear part of the element map. These equations are linear because I've neglected all the higher order terms, which one has to deal with in reality, but the most important concepts come from the linear theory. A linear map of the coordinates through some element of the ring can be represented as a matrix if we neglect the changes of the fields around the edges. So we just assume that the K functions are constants piecewise in the magnets. In a dipole, it's equal to this. In a quadrupole, it's equal to the quadrupole gradients. Then the equations are actually like the simple harmonic oscillator within each element, and one can propagate x and px, or x and x prime, through each type of element of length L with a matrix. If you have a simple drift space, the simplest thing, the angle, of course, increases the value of x just in proportion to the length. So the matrix is just this. In a focusing quadrupole or a dipole, x and px vary like the harmonic oscillator. One can represent them like the transfer matrix like this. In a D quadrupole, the trig functions become hyperbolic functions, and vice versa. For the vertical plane, there are similar equations. I'll mostly use the horizontal plane to illustrate. In principle, these are 4x4 matrices, or 6x6 if we also include the longitudinal coordinates that I'm not treating at the moment. Okay, so how can we focus in both planes with the same magnets? Well, we now have to consider the extension to many elements. We build up the map for a whole lattice, which is a sequence of elements, thousands of them in the case of the LHC or RIC. By taking the composition of these maps or the products of the matrices in linear approximation like this. Note that each map MI is area preserving. Its determinant is 1. In general, there are other invariants which go under the name of symplecticity that you may have encountered in Hamiltonian mechanics. The nonlinear maps are symplectic, which essentially means that their derivatives are symplectic matrices at the origin. The determinant of the matrix is related to its eigenvalues. In our 1 degree of freedom example for X, the determinant of M is equal to the product of its 2 eigenvalues, and the 2 eigenvalues are inverses of each other. The 2x2 matrices generalize to 6x6 for X, Px, Y, Py, and so on. If they are, oh, sorry about the spelling mistake here, typo. They can be 2x2 block diagonalized to find the eigenmodes of the motion. I won't show all that formalism, but you can imagine how it goes from the 2x2 example. Of course, in reality, we use specialized computer programs. The one most commonly used at LHC is called MADX to compute the large and complex accelerator structures. The matrix formalism for the linear part is fundamental in the practical design work. Extensions to the nonlinear dynamics are done using, in some cases, Hamiltonian perturbation theory, Lie algebraic operator formalisms, and also in practice a lot of direct numerical tracking of particles in a kind of Monte Carlo approach to investigate stability. In linear approximation, we can look at the stability of transverse motion. What am I doing for time? Okay, already halfway through. Okay, I think that's about right. We require that the motion of all particles remains bounded after many turns around the ring. So any x, xpx can be expressed in terms of the eigenvectors of those matrices, like this. And after many turns around the ring, M being the transfer matrix of the whole ring, you will see that the initial amplitudes are multiplied by the eigenvectors to the power n. So if those eigenvectors have a modulus greater than 1, you have instability, the x will go to infinity. So since they are reciprocals of each other and complex numbers, their modulus must equal 1. They must lie on the unit circle in the complex plane, and therefore can be written as e to the I mu for some real quantity mu. If they move off, the only way they can move off the unit circle is if they collide here at with a real part of 1, and then they move, one eigenvalue moves inwards, the other one moves outwards along the real axis. You can show by manipulating the form of the transfer matrix that this condition for stability is the same as saying that the cosine of mu, which is equal to half of the trace of the transfer matrix, must lie between -1 and +1. In other words, the mu should not approach pi or 2 pi or 0. So an accelerator lattice can also be built up of many identical periods in a simple case. The stability criterion may be applied to each of them or to the whole ring. And since the trace is an invariant under cyclic permutation of matrices, the stability criterion is actually independent of the starting point in the ring, as you would expect from physical intuition. So let's see a little more how that works in a simple case of an accelerator lattice. And we can also use, for the sake of understanding and keeping the equation simple, the so-called thin lens approximation. That's the limit of elements with constant strength. So in the case of a quadrupole, its integrated strength is the gradient K times L. K, by the way, comes in units of meters to the -2, as you can see by looking back at the definition. That's of course for a given reference momentum P0. It's a scaled version of the magnetic field, just as the analogous quantity in a bending magnet is the bending angle that it makes, which is the in the limit K of L going to 0 and K going to infinity, but you keep the product constant. So you lump all the integrated quadrupole strength in a very narrow lens. KL is actually 1 over the focal length of that lens. In thin lens approximation, the matrices for focusing and defocusing quadrupoles are very simple. They look like this. A basic element module for constructing circular accelerators, including the LHC, all the arcs of the LHC, for example, or RIC, or many other machines, are periodic so-called photo lattices. Photo comes from focusing quadrupole, nothing, or just a bending magnet, a defocusing quadrupole, and again, nothing, at a period that repeats like this. So here is an example schematically. This box on the positive side represents a focusing quad, this one a negative one, here again a focusing one. So between here, the centers of these two F quads, we have a single period of this lattice, which just repeats. And you have alternating quadrupole strengths like this. You can easily work out for yourself that the matrix for one period, if the lengths between the quads are L, is given by this. And you can check that the stability criterion for this period requires that F should be greater than half the length of the space between the two quadrupoles. So if you make the quadrupoles too strong, this machine will become unstable. If you make them too weak, the beams will be not very well focused and eventually become unstable again as well, because the weak focusing will overcome the vertical focusing. Actually, the dipoles are not shown here. This is the basic principle of alternating gradient or strong focusing, which has been the foundation of all circular accelerators since the late 1950s. I've tried to illustrate that in detail so that you understand it, because I think it's the fundamental principle upon which all our machines are based and may still be based for a long time to come, in my opinion. So in practice, we need some additional formalism, or which is not completely unique, but I will explain the form that is used most commonly, because it's a language that you will hear people speaking, and it's good to have some understanding of it. We describe these transverse motions in terms of optical functions. Sometimes people call them twist functions. You've heard of Hanbury, Brown, and Twist. It's the same person, although I don't know why his name is associated with these functions, because he didn't. It wasn't him who introduced them, and I don't think he especially wrote papers about them. Anyway, it's traditional, so you'll hear this terminology very often. The Hill equation, like this, is well studied in applied mathematics. You may have encountered Floquet's theorem. It's also somewhat formally analogous to equations that are used in solid state physics and crystal lattices. There's another canonical transformation that one can make in a formal Hamiltonian approach, which we won't use, but just go ahead with a sort of an ansatz of representing the solution X in this form with two constants of integration, essentially a constant J and a constant psi sub 0, a phase. If you're familiar with the concept of action angle variables, you may recognize what's going on here. This is the action angle transformation of the betatron motion in the accelerator. There is a function called beta of S, which is introduced here. We don't know what it is. This should have a subscript X for beta X. There's another one for Y. And there is a phase, which is a function of S. These are not, these are properties of the machine, the lattice of the focusing functions, and not of an individual particle, which is described by J and psi 0. So plugging this form into the equation and differentiating all the terms correctly, you will get something like this. If you equate the sine and cosine terms to 0, you get some equations which relate the beta and the psi functions. And you can quickly show that psi prime must be equal to 1 over beta. So psi is given by an initial value. Well, actually, I shouldn't have used the same notation for this and this. That's something different. This should be the psi at the point 0, which we can define to be 0, actually. Will be the integral over S of the 1 over the beta function. And then there is the beta function is described by this somewhat more complicated equation involving the K, the gradient function. And people normally introduce two auxiliary functions, alpha prime, which satisfies this equation and is actually equal to minus beta prime over 2, and sometimes a gamma, which you should not confuse with the relativistic gamma, which happens to be 1 plus alpha squared over beta. These notations just simplify some of the other expressions that come in. So as an exercise, you can check all the steps and also derive the equation for px, the derivative with respect to S of x. So this looks like a quasi-harmonic oscillator. The equation for P is a little bit more complicated. You will often hear people talking about the beta function, especially at the interaction point, but this is exactly where it comes from. By plugging these forms into the transfer matrices that we've already seen, it's a little bit of work, but you can convince yourself that you can parameterize the transfer matrix in terms of from point 1 to point 2, any 2 points in the ring, with the values of the beta and psi functions at those points, like this. You can see that if at the observation point beta 2, the X value will be large if the beta at point 2 is large. And if the initial value of X back at point 1, where it came from, is small, then it will also be large, and so on. So it's worth looking at this expression to understand the physical meaning of the factors of beta and how they propagate values of X around the ring. Generally, in a transfer line, a machine which is not closed, or a linear accelerator, you can just give an initial value for beta and propagate its value throughout the whole accelerator lattice. In a circular machine, you can get a unique value of beta, which is special, by imposing the periodicity condition, and that's particularly significant. The one-turn transfer matrix from a single point, such as, let's say, the Alice interaction point, through a whole turn back to the same place, can be written simply in terms of beta at Alice and the alpha and gamma functions I mentioned on the last slide. It's something like a rotation matrix, but a little bit more complicated. And we can identify the parameter mu in the stability conditions we mentioned earlier with the phase advance around the ring psi. And it's conventional to define the so-called tune as the betatron wave number around the whole ring, the number of these betatron oscillations around the ring. So it's psi divided by 2 pi, which is also the integral of the inverse of the beta function. This tune function in the horizontal plane at the LHC has the value 62.30. Sorry, that should say QY, and 60.32. And there are elaborate systems in the LHC devoted to maintaining precisely these values with feedback. And these values are monitored very closely in all accelerators because their values are very important. I'll show you why. If you generalize the theory to, well, no, let's stay with the linear theory. The instability conditions mentioned above corresponding to the tune becoming equal to an integer or a half integer, then the transfer matrix becomes unstable. The eigenvalues move off the unit circle. But more generally, when you treat the nonlinear theory and all the nonlinear terms in the equations of motion, and there are plenty of them, these are due to the sextupole and octupole magnets that we introduce, but also due to imperfections of the magnetic fields, which are more of a concern in superconducting machines, and they vary in time or with the magnetic field strength as you ramp the machine. So it turns out that in the most general case, any integer linear combination of the two tunes, if that is equal to another integer p, that defines a line in the QX-QY plane. And if you start drawing these lines, you start to get very worried very quickly because they are everywhere. And they form this web of resonance lines. You have, in a beam, you could have a spread in tunes, which in this example is illustrated here. This isn't the LHC, it's just an example I found. It's very hard to avoid these resonance lines. So one has to devote a lot of attention to the terms in the Hamiltonian that drive different resonances and find places where you can actually operate your machine. In the LHC, it's a very delicate matter. That's why I said there's a lot of attention paid by the operators and feedback systems to maintaining the correct value of the tunes. I can't treat perturbations of the ideal machine in much detail. I'll just give a generic example, which is a quadrupole perturbation. Real machines are never perfect as designed, and there are many kinds of perturbations, not only misalignments of the magnets, which can cause perturbations of the closed orbit. The true closed orbit of particles is not the same as that reference curve, but also the motion becomes nonlinear, and more so as you increase amplitude deviations from the reference closed orbit. But just consider a generic perturbation, which is the insertion of a single small thin lens quadrupole in a ring whose twist functions or optical functions are matrix M0 from the same point we already know. So the transfer matrix would be equal to M0 in the absence of the perturbation, but you slip in this perturbation, this little quadrupole here, and it's changed to the product of these two matrices. And you then find that the tune will be modified by this quantity, which depends on the local value of the beta function. And so you have what we call a tune shift in our jargon, which is beta 0 over 4 pi times the focal length, which is 1 over the k times the L of the quadrupole. So this shows you generically that the beta function measures the sensitivity of the optics to a generic perturbation. So places with a large beta function are liable to cause you trouble. We already saw that the beta function also provides a measure of the amplitude of the oscillations, which comes into the relative size of the beam in different places. So you would like to avoid large values of the beta function, but we'll see shortly that this is hard. The design of an accelerator ring optics is usually concerned with providing a suitable form of the beta functions in both planes to achieve design goals. Analytic understanding of special cases such as the photocell or focusing triplets around an interaction points those are useful guides, but this is actually a multi-parameter optimization process, which is actually quite an art and quite difficult in some cases. It's called matching in optics, in our jargon, and it's quite can be quite complicated. I'll show some examples later. This is the optics of a photocell. You see this one has bends in it, and you see the F quadrupole is split in two to provide a start and end of a symmetric period. And here you have a D quadrupole in the middle. This is in a smaller machine, like a light source. Sorry, was there a question? Or?
No.
Oh, okay.
You have 10 minutes for today's class.
Okay, I might overrun slightly. I hope not too much. There's another function dx, which I'll mention later, which we often talk about, also called the dispersion. Another concept that you will hear much about is the emittance of a beam. In the Hadron Collider, this is a measure of the beam quality. Beams have a transverse size and divergence, which is a spread in the transverse momenta or the angle of the trajectories of particles in the beam. The horizontal emittance is defined by this expression in general, in an uncoupled case, which is actually equal to the mean of the J, the action variable of the beam. And in the case of an upright beam, it's the product of the sigma x and the sigma y, if you like. This averaging denotes an average over all particles in the beam. A particle with a given J will, at a given point in the ring, will move on an ellipse like this, according to the equations we saw. And A is actually, sorry, in this case, 2J. The area of this ellipse is pi j. Sometimes the emittance, people write the emittance with an explicit factor of pi. So they say it's pi times so many micrometers, typically. There is also an invariant emittance, which I'll define tomorrow, which is more often mentioned at the LHC. This one is called the geometric emittance. Usually at the LHC, we use an RMS definition. Those of you working at RIC might have to be careful because they use another definition such that I think it's 90% of the particles fall within the emittance ellipse. And you should also be aware that the emittance is a property of a beam, many particles, hence the averaging, not of a single particle, although some introductory treatments call the amplitude J or A the emittance. This is frowned upon. So in a matched linear focusing system, where the beta functions are periodic as designed, with no coupling, each emittance is preserved, and this is a consequence of Liouville's theorem projected into each degree of freedom, x, y, and the longitudinal one. I don't have time to treat longitudinal motion. It's theoretically analogous, but in practice quite different to the extent that it's mostly handled at a hadron machine by people in a different group, the RF group, rather than the beam physics group. Although, of course, there are many interactions between not only the equations, but the people. I'll just make some statements which I hope give you a superficial understanding of the longitudinal motion. Particles a given particle may not have exactly the correct momentum. Its momentum P is equal to the reference momentum times a factor 1 plus delta. Delta is a fractional deviation of order 10 to the minus 3 or so. A particle with a higher momentum is bent less by the magnets and so travels on longer paths towards the outside of the ring. It's the effect of the speed of the particle we'll neglect because we're thinking about ultra-relativistic particles. As you go down in energy, the velocity of the particle will also change. So there will be another effect counteracting the fact that the path and therefore the time taken to go around the ring is longer. But if the particle is slightly faster, if it's non-relativistic, this may be compensated. There's something called transition energy where both these effects exactly cancel. And that's a complication. Heavy ion beams in the SPS, for example, have to cross this special energy. I won't discuss that though. Anyway, these paths are modified by the focusing. I could add the perturbation due to the momentum change into the Betatron motion equations, and there will be another term. And the solution then takes a new form where there's another function introduced. It's usually called D, sometimes eta, called the dispersion, which is proportional to the value of delta for a given particle. As I said, this lengthens the revolution period. And this has to be counteracted by longitudinal focusing. What does longitudinal focusing? Well, here, this is where we start to need electric fields which come from the RF cavities. These accelerate or decelerate the off momentum particles, creating analogous oscillations of momentum or energy and the lag time with respect to the reference synchrotron particle. Now, there is only one place in the LHC where these lenses, the RF cavities, are installed, unlike for the betatron motion where there are lenses all around the ring. The oscillations are correspondingly much slower. The tune value of synchrotron oscillations is not of order 60, it's order 10 to the minus 3, typically something like 0.002 in collision. What this does is it bunches the beam, it focuses the beam in time and energy within one RF wavelength. Now, there are 35,640, the so-called harmonic number RF wavelengths around the LHC circumference. So these each provide a so-called bucket, which can contain a particle bunch. So that should all be described in terms of the proper equations. It's not very difficult, I just don't have the time, but I hope that's given you an intuitive understanding of the longitudinal motion. Now, I just want to illustrate a little bit how these concepts apply in the case of the LHC. This is a schematic orientation of the LHC. You can see that there are actually two beams. The reference curves for these two beams are a little more complicated than I showed earlier because they flip from the inside to the outside of the ring. Beam one, the blue one, in the arcs, these are actually separated by 18 centimeters in the twin aperture magnets of the arcs. There are two beam pipes. Of course, this is exaggerated in this schematic diagram, but beam one goes on the outside of the ring from point 1 to point 2, from Atlas to Alice. Beam two goes on the inside on a very slightly shorter path. So the S varies between 0 at point 1 and following beam one's blue path back to the circumference C, the 26.7 kilometers. By the time you get back, you can check that beam two, which goes this way, has exactly the same circumference length. There is still enough symmetry, basically left to right in this picture, that remains the case. However, although S at IP1 is 0 by convention for both beams, these arc differences tell you that the S value at IP2, the Alice interaction point, is different by about 15 centimeters. So I want us to be careful about these things. Here are the optical functions, the beta functions, and the dispersion functions in the interaction region of Alice. Okay, I've adjusted S equals 0 for technical reasons in this particular plot. But here is the Alice interaction point. You can see that this is the optics used in 2018 in the heavy ion run. You can see that the beta functions, beta x is blue, beta y is red, solid curves, go down to a very small value, which is actually 5 centimeters only. This is a scale of kilometers. At the IP, this makes the focusing that we want to increase the collision rate. You can see that there are some very strong quadrupoles around the triplet of focusing quadrupoles around the interaction point, which achieve this focusing. There are some other quadrupoles along here and along here, which arrange to match the interaction region beta functions to the periodic photocell, like the photocell example I showed you earlier, which the photocells start here with the bending magnets, some distance from the interaction point, a couple of 100 meters. And they continue all through the arcs in this periodic way. So you see the periodic solutions that you saw before. I mentioned that we don't like large values of the beta function, but we have some extremely large ones here in order to achieve the very small ones here. One thing comes with the other. The beam divergence is very large at the IP, it's very small here. You can see that the beta functions are not symmetric even because the blue boxes represent the focusing quadrupoles, the red ones are defocusing, and the flip between left and right actually flips X and Y. Why is that? Because if you look at beam 2, it's the other way around. And in the common section of the machine, you actually have the relatively difficult problem of designing two optics with the same quadrupoles, the same physical quadrupoles, except that they are a focusing quadrupole for beam 1 is defocusing for beam 2 and vice versa. So that's why you have this left, right, and XY permutation symmetry. Unfortunately, that's only approximate because of other practical considerations and the fact that IR2 is used as an injection insertion. The beams are injected here. Beam 1 is injected here and goes along the machine there. So there are other constraints on the design of these optical functions. So it's actually one of the most complicated examples that you will find in any accelerator. So that gives you an idea. You see other elements around the IP. Alice, of course, is in here somewhere. So it's not represented as in itself. The Alice solenoid, I didn't discuss how solenoids affect the beam. In general, they couple X and Y motion and have to be decoupled. And that coupling has to be undone by some skew quadrupoles somewhere else in the ring. So the motion is slightly coupled. In beam dynamics terms, actually, the Alice solenoid, even the Atlas solenoid or the CMS solenoid are quite weak as perturbations, as couplings, compared to the strong solenoids in a smaller collider like Daphne, for example. So just to illustrate, this is a simplified plot showing beta X in the Alice interaction region. I took it out of the previous ones. And mu X, the phase function, modulo 2 pi, which changes by several integers over this, well, a couple of integers over this region. So if you construct a trajectories, for example, square root beta times cosine 2 pi mu. Okay, I think I've changed convention for mu, so it's got the 2 pi's factored out. This is the mu that you get from programs like MADX, which I was using for this calculation. This is a typical trajectory shape without its amplitude quantity. This would have square root units of square root meters, which I don't show, but it shows you the shape. This is, again, the shape with an initial phase equal to 0, where we add an initial phase in here. Now, the particles in the beam can have all possible values of this initial phase, even if they have, if we just consider the ones with the same amplitude. So if we allow that phase to vary, you see that the combination of the form of the beta function and the well, let me try to replay that again because it was quite quick, shows you that the trajectories themselves do not follow the beta function because of the phase. They're varying more quickly, and depending on the individual particle's phase, it has quite a different shape. If we plot a number of those particles with equally distributed over 0, 2 pi in phase, we plot all those trajectories together, you get something that looks like this, and you can see that this is fleshing out what we call the envelope of the beam, which is given by square root of the emittance times beta X. So this is the overall shape of the beam as it in the horizontal plane, as it in the neighborhood of IP2 Alice. Here's a more elaborate plot which shows the horizontal size in blue and the vertical size in red, according to the complicated form of the beta functions that we had there. You can see in the case of Alice in physics in 2018, we also had the blue and red lines in the middle of the beam envelopes actually show bumps that we arrange by small dipole magnets in the orbit. You can see that we put in some special bumps in the orbit out here. And this is due to some nuclear physics that I'll talk about tomorrow. And you can see the very large beams. This shows, I think, 5 sigma of the beam. And you see that one has to start worrying about how the beam fits into the aperture. It's another reason why we cannot allow extremely large values of beta. So these very large values limit how small you can make the beta at the collision point, and therefore the collision rate or luminosity. There are also, okay, in the next picture, I'll show the vertical plane. So we aim for small beta at the interaction point, but we have to watch out for a number of things. As I said, large beta is also bad because any errors in these quadrupoles or any other nonlinear fields will have their effects amplified. So one has to take care that perturbations arising from unknown or error fields in these quadrupoles can have a large effect. This is the vertical plane where things are even more complicated. We have bumps in the horizontal orbit in Alice. Actually, there is a combination of 3 closed bumps in the orbit arranged with small corrector magnets, small dipole corrector magnets. One of these compensates the magnetic field of the Alice spectrometer dipole, which of course then is part of the bump in the vertical plane. It's a vertical field. Other compensator magnets compensate it. We arrange for a vertical crossing angle of the beams to avoid, because the bunches are coming with a certain distance between them. And if we didn't arrange an angle like this, there could be collisions of other bunches. The following bunch, one bunch of beam 1, which is going this way, would meet other bunches of beam 2 at some of these places marked with these dashed lines here near the collision point, and those beams would interact and potentially cause instabilities, which is bad. So we need this crossing angle. All modern colliders with many bunches have a crossing angle. And in 2018, we also had to lower the collision point by 2 millimeters because Alice sank into the ground a bit, and this had to be compensated. This should be fixed for run 3. I guess I might be running over time. Is it okay if I take a few more minutes?
Yeah, it is. You can
finished.
take 2 minutes only, I think.
This is a 3-dimensional picture of the beam envelopes in the collision with the beam pipe. It looks like this. This is the quite different looking picture that you have at injection energy. This is not so much a concern for the experiments, but to inject the beams where they have a lower energy and are therefore more subject to perturbations, we cannot allow them to collide. So we separate them with bumps in the horizontal plane also. They show the envelopes. And these separations have to be maintained during the process of accumulating beams of injection, which takes half an hour or more, the energy ramp, and then the squeeze, which is the process of transitioning from this optics through a number of intermediate optics, varying the beta functions in a smooth way, and many intermediate solutions have to be found by matching, as I mentioned. So there's a whole series of optics through which the beam transitions to get to the physics conditions, and then those bumps have to be manipulated in a safe way at the same time. A lot of setup has to be done, and then only then can we collide the beams. So as a summary of this lecture, using the simplest possible but still meaningful, I hope, approximations, we introduced the basic concepts of the coordinate systems, single particle motion and the optical functions, ideas of stability of motion and perturbations, a quick intuitive description of longitudinal motion, and the concept of the dispersion function, and the example of the Alice interaction region and beam envelopes. So tomorrow I'm not going to be so formal. There will not be so much mathematics. It's not I don't think the mathematics was too hard, but it was a little certain amount to get through in a talk like this. There will be less of that tomorrow. I will survey more practical items, the performance, the luminosity, and the things that limit it in collider operation. So thank you for listening, and I'm pleased to take questions.
Thank you, Professor Jowett. So now, actually, we are running late today, so I can take.
Sorry.
Yeah, no problem. One quick question, if you have. Otherwise, you can write to us or Siddharth, and tomorrow also you can ask Professor Jowett. Yeah, any quick question? Anyone from the student? If not, then thanks, Professor Jowett, for today's lecture. And your second lecture is tomorrow at the same time, 2 p.m. Indian time. Okay.
Okay.
Thank you.
Thank you. I'll stop share and put the slides on.
Yeah, it's okay. Thank you. So I cannot give some time to the students because we are already running late, and today at the end we also have this special lecture by Professor Nuzu, so we have to continue. So now this second lecture will be delivered by Dr. Subhash Singh. Subhash actually did his PhD from VCC Kolkata, and then from NISAR actually he finished his work working with Professor Bedangudas Mohanty, and then he worked on in Alice experiment during